Hi, my name is Mrs. Littell, and I will be going over Section 7.4, which is mathematical induction. And for mathematical induction, we have a couple of steps that we need to do. And the first thing is we have to show that it's true for the first value, or for n equals 1. The second step, we are going to show that it's true for k plus 1. And in this step, we have kind of a sub-step between those where we're going to assume that it's true for n equals k. And then we show that it's true for k plus 1. I've outlined what you're going to do on each of the steps here. For the first step, you're going to plug in 1 and show that it's true. Okay. On the second step, you're going to plug in k plus 1 to the left side. So that means we're going to add the k plus 1 on the left side. On the right side, we're going to replace k with k plus 1. Okay. So the left side will be partially replaced with the original term. And then we're going to add the k plus 1 term in there. And on the right-hand side, we're just replacing k with k plus 1. And then we're going to factor and show that they're the same on both sides. For the sum of powers of integers, there's formulas provided in the lesson. And you want to make sure you follow the order of operations. And we'll go through an example there. We're also going to cover an example on divisibility. So my first example is to show that the statement is true using mathematical induction. So we're given a sequence 2 plus 4 plus 6 plus ... plus 2n, and we want to show that it's true for n, it's equal to n squared plus 1. And we want to show that it's true for all positive integers, meaning we want to show that it's true for k plus 1. So following our steps, we need to show that it's true for n equals 1. On the left-hand side, that you can see that our first term is 2, because 2 times 1 is 2. On the right-hand side, if we plug in 1, we have 1 squared plus 1, which gives us 1 plus 1, which is 2. Step 1. The second step is that we want to first assume that it's true for n equals k. Okay, and this is going to allow us to show that it's true for k plus 1. So in this step, I'm just going to go ahead and rewrite the original with a k, because our next step is going to be to show that it's true for k plus 1. So we want to just be consistent. Okay, and now we want to show it's true for the k plus 1 term, which means that we want to show that it's true if we add one term. On the left-hand side, I'm going to show how I'm going to do this by using two different colors. We have 2 plus 4 plus 6 plus ... plus 2k, so that was our original. Now we have to add the k plus 1 term. I'm going to go ahead and add that in red. And that means I take the previous term and then add the next term, which is where the k was, we're going to replace it with k plus 1. On the right-hand side, we replace each k with k plus 1. So it's a little different on each side. The left side, you add the k plus 1 term. The right side, you replace k with k plus 1. So I used two different colors on this left side so that you could see that this whole thing here is exactly what we had here, and we know what it's equal to. We know that this part is equal to k squared plus k. And that is what we're going to replace it with, so that we can show that it's true for k plus 1. So that whole first part, I'm going to highlight it for you, was my original, which is here's the original, and this is what the original is equal to. So I replace it with the original value, which is k squared plus k. That means that I still have my k plus 1 term, which is the plus. We're going to have 2 times k plus 1. Okay, and on the right-hand side, I'm just going to go ahead and multiply this out so that you can see what we're trying to get towards. Okay, we first have to FOIL. So we have k squared plus 2k plus 1 plus k plus another 1. So our right-hand side becomes k squared plus 3k plus 2. Now let's see what our left-hand side is. If I redistribute, I have k squared plus k plus 2k plus 2, which is k squared plus 3k plus 2. And you can see that the left side is equal to the right, so that we've now shown that it holds for all positive integers. Okay, I think the most important step that it's hard to see is replacing this original with what the original is equal to, and then adding the k plus 1 term. All right, next we're going to use the formulas to find the sum of the integer, the sum using the formulas for the sums of powers of integers. Okay, so here I think that what it's hard to see is what n equals and which formula to use. Okay, so down here, this is going to tell us what power we have. So in this case, our power, and I don't know if you can see this, but the sum, it's the sum from n equals 1 to 5 of n to the 4th power. So our power is 4. So that means we're going to have to use the formula for the 4th power, which is right here. And this is from your lesson. So, and now in this formula, the n equals the number of terms being summed. And in this case, we're summing 5 terms, because on the top, or from the value 1 to 5 means there's 5 terms, so n is 5. Okay, so I think that's where sometimes there's a mistake made. So n times parentheses n, which is 5, plus 1, 2 times 5 plus 1, 3 times n squared plus 3 times 5, which is n plus 1, and we're dividing by 30. If I simplify this, this is 5 times 6 times 11 times, now this is 25 times 3, which is 75, plus 15, and my formula, this is actually minus 1. I wrote it wrong. And if we combine those, we get 5 times 6 times 11 times 89, divided by 30. 5 times 6 is 30, so I can cancel those. And then we have 11 times 89, which is 979. So the other way you can do it is just to go ahead and multiply 1 to the 4th, plus 2 to the 4th, plus 3 to the 4th, plus 4 to the 4th. You can do that, but this is a shortcut. And this is also using the formula. Take note that you need to follow order of operations. I think a key is where it has 3n squared. A lot of people do 3 times n first and then square it, but only the n is being squared. Notice I only squared the 5, which was 25, and then multiply by 3. You should get 979. Next, let's show that 3 is a factor of n cubed plus 2n. And you saw this in your lesson. It also mentioned it in the textbook as well. Okay, to show that it's a factor of n cubed plus 2n, we have to assume that 3 is a factor of n cubed plus 2n, and we want to show that it's true for all values. So we're going to use mathematical induction, just like before, which means we need to show that it's true for n equals 1. If I plug in 1, I have 1 cubed plus 2 times 1, which is 1 plus 2, or 3. Now is 3 divisible by 3? Yep. So it's true for n equals 1. Next, I'm going to assume that it's true for n equals k. So I'm going to replace this with k cubed plus 2k. And the last step is to show that it's true for k plus 1. So what I need to show is that once I add the k plus 1 term in there, that 3 is still a factor. Okay, when I do this, I'm going to have k plus 1 quantity cubed plus 2 times k plus 1. K plus 1 quantity cubed is k plus 1 times k plus 1 times k plus 1. And we still have 2k plus 2. Okay, if you go ahead and FOIL this out, you'll get n cubed, or I'm sorry, k cubed plus 3k squared plus 5k plus 1. That's just multiplying. This is k squared plus k, so plus 2k plus 1. I FOILed those two together, and then I multiplied by the k plus 1. So if you do that, you get k cubed plus k squared plus 2k squared, which gives us 3k squared, plus 2k plus k, which is 3k, should be 3k, plus 1. And then you have plus 2k plus 2. Now, this is a little messy, but that is a 3k. When you combine them together is when you have k cubed plus 3k squared plus 5k plus 3. Now we haven't shown that it's divisible by 3 yet. What we want to do is we want to get the original term, because we know that that's true, and then we want to break that up into a smaller section so that we can show that it's true for both. So if I break it down to my original, which was k cubed plus 2k, then I'm left with 3k squared, I'll do this in green, plus, now if I take 2k away from here, I have 3k left, and I still have 3. So these two statements are just equivalent. I just broke them up into two different statements so that you can see that this is the original, and this is the second part that we've added on. We know for the next part, if we factor out of 3, then we have k squared plus k plus 1 left. But the most important thing is to see that there's a 3 out in front. And we know that 3 divided by 3, so this one works as well. So we just proved that it's divisible by 3, because 3 goes into the first part and the second part. So together, it is divisible by 3. Hopefully this gives you a better understanding on how to use mathematical induction. We've shown divisibility. We worked on the sums of powers of integers, and we also did a proof by mathematical induction. If you have any questions, you can contact me or your instructor. My email is in the chat box. It's jwattel@flvs.net. I hope this gave you a better understanding so that you can now go and complete the assessment.